Imagine if airplanes could heal themselves, just like our skin does after a cut. Self-healing materials are making this a reality, giving aircraft the ability to repair tiny cracks before they become dangerous. These materials act like an immune system, detecting and fixing damage automatically, even during flight. This technology could revolutionize aviation safety, reducing the need for constant inspections and costly downtime. We'll explore how these materials work, from healing capsules to smart polymers, and why they're crucial for safer, lighter and greener planes. The future of flight is inspired by nature's own healing powers. Let's see how self-repair is changing aerospace engineering. The blueprint for self-repairing airplanes borrows from nature like bones that heal after a fracture. Engineers embed repair mechanisms into lightweight composites, ready to activate when damage occurs. Microcracks from stress and fatigue are the main threat. Self-healing materials stop them before they grow. We'll break down what self-healing materials are, how they work, and the different technologies behind them like healing capsules, smart polymers, and electric repair systems. These innovations promise safer flights, lower maintenance costs, and longer-lasting aircraft. By learning from nature, we're making aviation more resilient and sustainable. Let's dive into the science behind this breakthrough. Self-healing materials are engineered to sense and repair damage automatically, no human needed. When a crack forms, it triggers a built-in healing response like dominoes falling in sequence. This could be capsules releasing a sealant, fibers bleeding a repair agent, or molecules reforming bonds. The goal: fix microscopic flaws before they become big problems, keeping aircraft strong and safe. It's a proactive approach, like a pipe that seals its own leaks before disaster strikes. These materials are vigilant guardians, maintaining their own integrity. That's the science behind automatic repair in aviation. Nature is the ultimate self-repair expert. Think of how skin heals or trees seal wounds with sap. Engineers mimic these processes, building aircraft materials with tiny vessels that deliver healing agents, just like a tree's resin. Bones remodel and heal themselves. Scientists are creating polymers that reform bonds when triggered, regrowing the material. By studying biology, we're not just copying nature. We're learning its secrets for resilience and longevity. The goal: materials that adapt and recover, making airplanes more like living organisms. This bio-inspired shift means building structures that manage and heal damage, not just resist it. It's about giving machines the wisdom of nature. That's the future of engineering. Self-healing materials are more than automatic patches. They're intelligent, with built-in memory and instructions. Shape memory polymers can revert to their original form when triggered, erasing dents and cracks. Some materials use reversible bonds, reconnecting at the molecular level when heated. The latest advances combine self-healing with self-monitoring. Fiber optic sensors detect damage and trigger repairs. These smart materials can communicate with aircraft systems, reporting their own health in real time. The vision materials that detect, report and repair over and over, like living tissue. This is the next leap in aviation safety and intelligence. One of the most well-developed approaches to self-healing is the microcapsule method. Think of it as embedding a microscopic first aid kit directly into the aircraft's material. The process begins by creating millions of tiny capsules filled with a liquid healing agent. These capsules are mixed into the liquid resin used to create composite material. When damage occurs, microcracks rupture the capsules, releasing the healing agent. The liquid hardens, bonding the crack faces and restoring the structural integrity of the composite. The microcapsule system automates this process on a microscopic scale. It's a reliable way to stop cracks from growing, ensuring aircraft safety. Smart polymers, especially those with shape memory properties, have a memory of their original undamaged form. Applying heat unfolds the material, returning it to its original state. This is programmed into the material's molecular structure. Scientists are designing polymers with reversible chemical bonds. When a crack forms, these bonds break. Applying heat reactivates the bonds. They reconnect, restoring the material's structure. The material itself is the healing system, allowing repeated healing cycles. For aircraft, this could mean components heal repeatedly, increasing durability. Heat from air friction during flight could activate healing automatically. Thermal activation triggers healing chemistries, including shape memory polymers. Embedding thermoplastic materials into thermoset composites is one approach. Heat melts thermoplastic additives near microcracks, filling voids. Cooling solidifies the thermoplastic, bonding crack surfaces. Thermal activation's precision allows targeted heat delivery. Embedded conductive elements enable localized joule heating for efficient repairs. harnessing heat from flight or ground systems, maintains aircraft structures, extending lifespan and enhancing safety. Researchers are exploring electrically activated healing, using electricity to trigger repair, offering unparalleled control and speed. The key is making aircraft material electrically conductive by embedding nanomaterials like carbon nanotubes. These particles form a network, turning insulators into conductors. Damage disrupts this network, causing measurable resistance changes detected by sensors. A low-voltage current is applied, generating localized heat, triggering a healing reaction. Electrical activation's precision delivers energy to microscopic areas, ensuring efficient repair. This enables automated, closed-loop systems. Electrically activated healing combines sensing, diagnosis, and repair. Aviation applications are immense, especially for stealth aircraft and drones. By giving materials an electric touch, engineers are creating intelligent, self-aware aircraft structures. Safety has always been the #1 priority in aviation. However, metal fatigue and material degradation remain a persistent challenge. Self-healing materials can revolutionize aircraft safety, acting as a 24/7 defense system. They address problems the moment they arise, repairing damage long before it compromises the aircraft's structure. Think of it like having microscopic mechanics constantly patrolling for damage and fixing it on the spot. This reduces the risk of structural failure during flight, adding a powerful new layer of safety. It's an elegant and effective solution, making air travel even safer. Self-healing materials offer a powerful economic advantage. Maintaining aircraft is complex and expensive. Airlines follow strict schedules, taking planes out of service for inspections. Downtime is a significant cost. Self-healing materials could change this. By automatically repairing minor damage, these materials reduce wear and tear, extending maintenance intervals. More flying time and enormous cost savings would be achieved. Self-healing materials perform a seamless repair, restoring properties without adding weight or creating weaknesses. This could lead to condition-based maintenance, where repairs are performed only when needed. This data-driven approach would save billions while running a safer fleet. Self-healing materials can improve future aircraft design. Lighter aircraft require less fuel, reducing costs and emissions. Currently, aircraft are over-engineered for safety. Self-healing materials allow engineers to design with more confidence and reduce safety margins. This reduces structural weight, allowing for more passengers or less fuel. They also extend the lifespan of aircraft parts. Fewer parts need manufacturing, reducing raw material and energy consumption. Ultimately, self-healing technology enables safer, cheaper, more efficient, and environmentally responsible aircraft. Leading aircraft manufacturers like Airbus and Boeing are actively pursuing self-healing technologies. Airbus, in collaboration with the University of Sheffield, is developing composites with microcapsule healing methods for aircraft like the A350. These materials automatically fix cracks, sealing damage from the inside. Boeing is exploring smart polymers that react to pressure changes, autonomously triggering a sealing reaction to maintain structural integrity. This technology aims to create lighter, more durable, and fuel-efficient aircraft, enhancing safety for future commercial aviation. NASA faces immense challenges operating vehicles in extreme space conditions. Spacecraft endure intense radiation, temperature swings, and micrometeorite impacts. NASA pioneers self-healing materials, essential for long-duration space exploration. Research focuses on polymers that mend themselves after punctures or radiation damage. One concept mimics blood clotting using polymers that rapidly solidify to plug holes. NASA investigates materials that withstand atomic oxygen and UV radiation. These technologies benefit high-altitude aircraft, increasing resilience and mission effectiveness. NASA's work paves the way for safer, more robust aviation. In military aviation, aircraft must withstand damage to complete their missions. Military aircraft, especially drones, operate in dangerous environments. Defense contractors like Northrop Grumman invest in self-healing technology to enhance aircraft survivability. A plane that can repair itself mid-air is a more resilient asset. Research focuses on self-repairing systems, including materials that seal punctures. This technology is compelling for drones on autonomous missions. Self-healing systems allow UAVs to absorb damage, repair themselves, and continue. This provides a significant tactical advantage. It transforms aircraft into recoverable platforms. Self-healing technology is about building survivable aircraft for future operations. When we think about self-healing, our minds jump to comic book superheroes like Wolverine. No matter the injury, his mutant healing factor kicks in almost instantly. This idea of near-instantaneous regeneration is the ultimate goal for self-healing materials. The next generation aims to create structures that heal themselves as fast as they are damaged. Imagine a material where a crack is sealed the very microsecond it forms. It would actually prevent the wound from ever truly opening in the first place. An airplane with this capability would be perpetually in its prime condition. The Wolverine analogy serves as a powerful inspiration, setting a clear target for what we want to achieve. Envision a future where the materials we build with are as dynamic and resilient as the heroes we imagine. The future of self-healing materials will likely be found by looking even more closely at the designs that nature has already perfected. Bio-inspiration, the practice of learning from and mimicking strategies found in nature, will continue to be a primary source of innovation. Scientists are studying the remarkable regenerative abilities of organisms like starfish, which can regrow entire limbs, or salamanders, which can regenerate complex organs. They're not just looking at the what but the how, the underlying genetic and cellular instructions that orchestrate these incredible feats of healing. The goal is to translate these biological principles into the language of chemistry and material science. This deep dive into biology is leading us into the realm of nanotechnology. The future of self-repair may not involve capsules of liquid but rather swarms of tiny nanobots or nanostructures embedded directly into the aircraft's material. Imagine millions of microscopic robots, each programmed with a simple task: to detect a structural anomaly and work together to repair it. When a crack forms, these nanobots would swarm to the site, carrying atoms or molecules to rebuild the broken structure from the ground up, much like how cells work to heal a bone. This would be a truly living material, capable of not just healing but actively reorganizing and strengthening itself in response to stress. Another bio-inspired concept is the creation of a vascular network within the aircraft's structure. Just as our bodies have a circulatory system of arteries and veins to transport blood, future aircraft composites could be interwoven with a network of microscopic hollow channels. This network could circulate a multi-part healing chemistry, constantly ready to be deployed. If damage occurs, the system could pump the necessary components to the site to perform a repair. Even more impressively, this vascular system could also serve other functions, such as thermal regulation to cool the aircraft's electronics, or de-icing the wings in cold weather, creating a truly multifunctional, intelligent material. By combining the genius of biology with the precision of nanotechnology, we can create materials that are far more sophisticated than what we have today. These future systems won't just perform a simple patch, they will carry out a complex, orchestrated regenerative process. They'll be inspired by the elegance of human skin, the resilience of tree bark, and the regenerative power of bone. This approach will lead to aircraft that are not just machines but are closer to being living organisms, with an innate ability to sense their environment, respond to injury, and maintain their own health over incredibly long lifespans. The ultimate evolution of self-healing technology is its fusion with artificial intelligence. The future is not just a plane that can heal itself, but a plane that can think about its own health. We're moving toward the concept of a sentient airframe, a structure that is fully self-aware. This involves embedding a dense network of advanced sensors throughout the aircraft, capable of monitoring everything from stress and strain to temperature and chemical composition in real time. This massive stream of data would be fed directly to an onboard AI processor dedicated to structural health management. This AI would act as the brain of the aircraft's body. It would constantly analyze the incoming data, building a complete and dynamic picture of the airframe's condition. It would be able to detect the formation of a microcrack far earlier than any sensor alone by recognizing subtle changes in stress patterns. More importantly, the AI would be able to make intelligent decisions. It could assess the severity of the damage, determine the best course of action, and then activate the most appropriate healing mechanism. For instance, it might decide a minor crack only needs a small thermal treatment, while a more significant issue requires deploying a nanobot swarm. This creates a powerful, closed-loop system of detect, diagnose, decide, and act. The aircraft would not only know it is damaged, but would also understand the implications and execute a tailored repair strategy, all without any human intervention. Imagine a plane flying from New York to Tokyo. During the flight, turbulence causes minor fatigue in a wing joint. The AI detects this, activates an embedded electrical system to gently heat the area, and triggers a polymer healing process. The repair is completed mid-flight, The AI then logs the event and reports to the ground crew upon landing that a successful self-repair was performed, confirming the structure is back to 100% health. This vision of a sentient airframe represents the pinnacle of aviation safety and efficiency. It would make mid-air maintenance a reality, drastically reducing the chances of accidents caused by material fatigue. Such an aircraft would be able to predict future problems based on its current wear patterns, allowing it to take preemptive healing actions before damage even occurs. This combination of advanced materials, nanotechnology, and artificial intelligence will give us airplanes that are not just healing like superheroes, but are also thinking like them. Always vigilant, always ready, and always working to ensure a safe journey. We've explored self-healing materials inspired by our own skin and advanced technologies in aviation. These innovations create airplanes that manage their own health, fundamentally rethinking how we build them. This technology enhances safety by stopping microscopic cracks, tackling material fatigue, promising a future where structural failures are a distant memory. Safer skies also mean a healthier planet and a more robust global economy. The age of self-repairing aircraft is dawning sooner than you might think. As we look toward the horizon, the future of self-healing materials seems bound only by our imagination. The concepts we've explored, from superhero-like instantaneous healing to bio-inspired vascular networks, are just the beginning. The fusion of nanotechnology, advanced materials science, and artificial intelligence promises to create aircraft that are more like living organisms than machines. We're on the cusp of developing sentient airframes that are fully aware of their own structural health, capable of detecting, diagnosing, and repairing damage all on their own. This represents a paradigm shift toward truly autonomous and resilient systems that will redefine what is possible in aerospace. This future is being built today in the research labs of companies like Airbus, Boeing, and Northrop Grumman, and in the forward-thinking programs at NASA. Their work is turning science fiction into practical reality, one breakthrough at a time. The real-world examples show us that self-healing materials are not just a theoretical dream. They're tangible technologies being tested and refined for commercial and military aircraft, as well as for the even greater challenges of space exploration. Each successful experiment brings us closer to a world where our most advanced vehicles are equipped with an innate ability to survive and thrive in the harshest environments. The ultimate lesson here is one of inspiration. The simple, elegant process of healing that we often take for granted in the natural world holds the key to our technological future. By observing how a tree seals a wound or how a bone mends a fracture, we find the blueprints for creating more durable, sustainable, and safer technologies. It encourages us to look at the world around us with curiosity, and to ask how nature's solutions can help us solve human problems. This journey into self-healing materials is a powerful reminder that some of the best ideas have been around for billions of years, just waiting for us to discover them. So the next time you see an airplane soaring overhead, think about its future. Imagine it as a smarter, more resilient machine, one that can patch its own wounds and constantly monitor its own health. This is the future that self-healing materials are building, a future where flying is safer, more efficient, and more in harmony with the principles of the natural world. It is an exciting time for science and aviation, and the sky is no longer the limit. It's just the beginning of what we can achieve when we blend human innovation with the timeless wisdom of nature.